So this morning we talk about the concept of tiling and blocking, and when you implement it for a real application and your own problem, there are a couple of things that you actually need to know so that you don't run into some unexpected problems. And one of the things that typically will go with tiling is actually something called thread coarsening. And so I'm going to introduce the concept, and then I'm going to put them together and show you how it actually works on a real application. So thread coarsening is really from the concept that when you do a very fine-grained decomposition of your computation, you would end up with these threads that are doing very little each. Okay, and when that happens, you could end up doing a lot of redundant work in every thread, just so that they can all run in parallel. And when the thread is doing very little work, the redundant work could actually be more than the real work it does. Okay, and this happens a lot in the very fine-grained parallelization. Programming models like CUDA or OpenCL encourage you to do this kind of fine-grained parallelization. Essentially, the kernel that you're writing is called elemental function in many circles. And there's a good reason why they're called elemental functions. These functions are typically written to process one element of your data structure. Okay? And when you write a function to process only one element of your data structure, the amount of code, amount of work that you have for each element will be small. Okay, and so if you start to have so much redundant work compared to the real work, then it becomes necessary to actually hold back a little bit. Okay, pull it back a little bit, and reduce the redundant work. The redundant work could be in the form of floating point operation. In the GPU's case, floating point operation tend not to be too much of a problem. But it could also be memory accesses. When that happens, then it becomes a bigger problem. So a good reason why we want to reduce redundant work is actually when you end up accessing memory in a redundant way when you decompose your problem to be very, very fine-grained. So what thread coarsening does is to merge multiple threads back together. Okay, you take these very fine-grained threads and merge them back together. And so that you can do the redundant work only once for the multiple threads that you merge into one. Okay, you take all their redundant work and you eliminate all but one of them. Okay, so that's the basic idea of thread coarsening. What I'm showing here is in order to perform, let's say, to do a parallel, to do the fine-grained parallelism, we decompose the work into 12 very fine-grained threads. However, our hardware is only able to execute 4 of the threads at the same time. So this particular decomposition is actually over parallel as far as the hardware resource is concerned. However, we ended up introducing redundant work in each thread as I mark as red here. So in this case, there's more redundant work than the real work, which is blue. The thread coarsening would do is to actually merge, let's say, these 3 threads into one, and take the redundant work and do the redundant work once, and then do the unique work. And in this particular case, I'm actually showing that you can even do it for a 2-way parallel system by merging 6 of them together. Okay, so this is fairly simple concept, but there are a few things that you need to know in order to avoid some of the common pitfalls, and it has to do with the data structure padding and so on that you need to do in order to use this properly. Okay, so we'll be going through all this today. the technique is fairly simple. Conceptually, what you're doing is you're taking taking multiple threads, and so that the resulting thread will calculate multiple output elements. The original kernel that you have is processing one element at a time. Okay, and the result kernel, after you're done with thread coarsening, will process multiple elements. And the way you can think about it is actually similar to loop enrolling. So you will take essentially multiple kernel function bodies and put them all into one function, okay? So that essentially you will be processing, you'll have the code to process the multiple elements. However, you will be eliminating the redundant work that were repeated in each copy of that work. So after you, the way you would do it is to do the redundant work once and store that into a automatic variable. And in CUDA or OpenCL, the automatic variable will be automatically mapped into registers so that you will be able to reuse the result of the redundant work for the rest of the function body. So that's why the merged kernel code will end up using more registers. Okay, and if you look at the trend, there is a trend of using more and providing more and more registers in these GPUs. The Fermi actually has twice the amount of registers compared to the previous generation. Yes, Rich.
It has fewer registers per core.
Per core, but actually more registers available per thread block.
It's a ratio of
Yeah.
counts, and that's
Yeah.
a big problem.
I agree with you. In fact, what Rich is saying is because the cores are getting bigger, so they're actually not necessarily getting more registers in that sense.
We've
Yeah.
been complaining to NVIDIA endlessly about
Yeah, and so this is actually one of the typical conversations that you will hear. Will continue to push these people to add more registers, and the reason why we need more and more registers is essentially this kind of code organization. Yeah, yeah, good. So there's increased efficiency may outweigh the reduced parallelism in the sense that when you use more registers, you could end up executing fewer threads. And if you're interested in this kind of work, just go online and search on Google and look for granularity. And there are quite a few recent articles about the fact that the fastest CUDA kernels tend not to be the finest granularity kernels. And one of the groups that have several articles about it is Jim Demo's group from Berkeley, and they repeatedly said, for most of the library code that they deal with, the highest performance kernels tend not to be the finest granularity kernels. And if you look at the code that they produce, they essentially apply thread coarsening to all their kernel code. So let me say a few words about register usage here. And it is probably obvious to most people who are familiar with hardware, but for application developers, this is oftentimes a very confusing topic. So let me try to clarify this. In the CUDA hardware or OpenCL hardware, there are registers and there are shared memory. And shared memory is actually called local memory in the OpenCL terminology. So many people ask me, what is the difference between registers and shared memory? There are a few things about registers. One is registers are extremely fast. Latency-wise, registers tend to be either comparable or somewhat faster than the shared memory. But that's not the most important for your performance. The most important part of register usage is it does not require a load instruction to access your data in the register. So for those of you who have learned assembly code programming, the machine instructions that use registers just mention the register number in the arithmetic or logic instructions. So that's why when you access a piece of data from your registers, you do not need to have an extra instruction in order to just get the data for you. Okay? Whereas shared memory is still a memory access. It requires a load instruction. Okay? And that load instruction is going to consume the instruction issue bandwidth. It's going to be competing for instruction execution slots with the floating point and so on. So that's why if you use registers, overall you will be getting higher throughput than using shared memory, simply because you don't need to use an extra instruction. Okay? You can save the instruction slot for other types of instructions. So it's fast, it gives you higher throughput. In fact, if you use ATI hardware, it's even more important that you use registers, because the registers, just the raw bandwidth out of the registers on ATI GPUs is even higher than their shared memory in that hardware. So those are the good things. The bad thing about registers is that the registers cannot be, the registers are private to each thread. So if you place a piece of data in a register, that piece of data is only available to the thread that placed the data in the register. Okay, so that's why we call it private. And threads cannot share computation results or load memory through registers. What we saw this morning was using shared memory because we're trying to share data across different threads, right? So here we have a very fast computation, very fast access, very high throughput, but we cannot share these data across different threads. So in order to use registers for multiple threads, if you know that your computation or data is redundant across multiple threads, and you want to use registers to eliminate that redundancy, then what you need to do in CUDA and OpenCL is to merge the threads, physically merge the code into a single kernel, and then use the registers. That's why this is an explicit transformation. And from all the indications, these things will be done by the compilers in the future. Okay? But we're still a little bit ways to go in terms of the implementation. So you know what? You still need to learn this. And even if you use the compilers, you should be still aware of this concept when you design your algorithms in the future, just so that you can use the compilers properly. I saw a question back there. Yes? Why doesn't index variables get into registers? Oh, are you talking, what are the indices? Are you talking about thread indices, or are you talking? Okay. Uh-huh.
I'm not sure, but I think those variables don't get into register.
Actually, I think they do. Nathan, I think those IJ variables actually get into registers.
Yeah, I believe so. The only thing that's been different in the past is that certain, like you could have a base register for an array.
Yeah.
And that would be in special register.
Exactly. Yeah. So the question, the answer is they should be. So you know, if you see otherwise, check with us. And there are some special cases in the past, and it may be a little too detailed for the general audience, but there are some base registers that used to go into some special registers because there's some hardware treatment kind of thing, right, for addressing mode.
The only other exception would be like if it's immediate.
Yeah.
Compiled.
Yeah. So you know what? Talk to us if you want to talk about more details. Yeah. You would disappear, exactly.
So if you had like a really small array, then you might see it disappear.
Aaron?
Yeah.
Yeah, what Aaron was saying is, if you have a loop and you have an index variable, if you unroll the loop completely, then that variable will disappear, and the compiler will replace all the proper constant values into the original positions. Okay, so let's talk about the direct Coulomb summation kernel with thread coarsening and register tiling. Okay. So essentially, the kernel, if you remember from yesterday, is calculating the contribution of all the atoms to all the potential grid points. So in this case, whenever we're processing grid points along the x dimension, then all these lattice points will only differ in their coordinates in the x dimension, and all of them will have the same z and y coordinates. So that's the reason why when we use input-oriented programming, we can be very computationally efficient, because we can just take an atom and then calculate the y and z components of the distance once, right? And then reuse all those values, right, for all these lattice points along the x dimension. And so I promised you that I was going to come back to this point, for the output-oriented programming yesterday, and this is when we're where we're going to address it. So for the gather-based kernel, or the output-oriented kernel, now we can coarsen the kernel by processing multiple lattice points in the kernel, okay, in the inner loop. So whenever in the original kernel, you will go through each thread will go through all the inputs, and then you will contribute the input effect to one output point. In a coarsened kernel, the loop will actually simultaneously process multiple lattice points. And so you will be accumulating the effect for multiple lattice points for each input atom, right? So that's the sort of the equivalent unroll that we're talking about. In fact, it's closer to a term called unroll and jam, if you are familiar with some of the high-level compiler transformations. Now, so what we can do is we can calculate if these 4 lattice points to be processed by that at the same time are all from the same x row, right? Then we can just calculate the y and z components of the distance once, and use them 4 times, right, or multiple times for the lattice points. So this is exactly what you're going to see in the code, and this is not exactly as efficient, computationally efficient, as the input-oriented code. However, after you amortize the computation 4 times, it's close enough. Okay, the effect of computation inefficiency is no longer really relevant in your performance. And sometimes you can even do it more times. But I think John Stone pretty much decided for this kernel, it's 4 times is pretty much as much as it gets. So because if you use more, you're going to actually use more registers. Okay, so at some point you're going to face a trade-off. And subsequent lattice points computed by each thread are offset by half-word to guarantee coalesced memory accesses. This is one of those things that you may or may not think about right away when you think about coarsening. The most intuitive way of thinking about coarsening is for each thread to process 4 consecutive lattice points in that x dimension. But that's not the best way. Remember, these threads are eventually going to write into the lattice points. So whenever they write into the lattice points, you want the neighboring threads to be writing into neighboring lattice points for coalescing reasons, right? So the way to do thread coarsening is actually to take lattice points that are multiple points apart. In this case, 16 in the most frequent case, because half warp is 16 in CUDA today. And then you can you have these points that are multiple points away, and you just then when you write out at the end of the computation, you'll have coalesced writes, coalesced writes, coalesced writes, and coalesced writes. Okay. And this also adds to some pain in terms of data structure padding. And I'm going to have a few slides that detail this. The loads and the increments, for the 4 potential lattice points from global memory will be done at the completion of the summation rather than the beginning. That is, essentially, you will be accumulating into 4 registers the effect that, of all the inputs. And then at the end of the computation, you will load the original lattice point value and then add the total into that lattice point value. And this reduces the register pressure. It's one of those details, but it's better for you to hear about it when, than discovering this yourself. Okay, so this is the piece of this is the code of the DCS kernel. It still iterates through the all the atoms, but for each atom, you will be calculating the Y component once, and then generate this this Z and Y component. Remember, the Z component will be coming through the parameter. And then you will be calculating the X components for all the 4 lattice points. And then you will be accumulating into 4 registers the contributions to these 4 lattice points. And that's why you'll be using more registers. Okay? So there's some considerations when you coarsen the kernels. One is, the good things is we can reduce the number of loads by reusing atomic coordinate values. And this is a little subtle, but if you look at the code, you see these 4 loads of atomic operation. The compiler will just fold them all into one. Okay, so the compiler would just generate 1 memory load into a register and then use it for all the 4 calculations. And this is very, very routinely done now. So that reduces the amount of memory access. Okay, so that's why I said redundant work doesn't mean that it's always calculation. It could be memory accesses. Okay. And by merging multiple points into one thread, we can compute the Y and Z distance component only once and use it multiple times. And this does add performance about 5% to 10%. And then a good balance between it achieves a pretty good balance between efficiency, locality, and parallelism. The downside is use more registers, and it increases the effective tile size. And this is a little subtle, so I'm going to use a few slides to talk about that. Remember, at the beginning of the lecture, I talk about DCS kernel and the course, and I say there's a SPMD programming model. So whenever the number of lattice points in each dimension is not a multiple of block size, right? Then we typically will be padding the data structure, enlarging the data structure so that it will be multiples of thread block size. And this allows you to write your code in such a way that you don't need to check whether you're out of bounds, right, when you process the grid points. And so in this particular case, let's say, I'm using a very small case. Each block has only 8 threads. And assuming that we have 4 threads in one dimension and 2 threads in the other dimension for the block. And if we have a 10 by 5 grid, then we need to extend it into 12 by 6, okay, to make sure that we're multiples of the block size in every dimension. And this adds about 44% overhead in terms of your memory usage, okay? And so for larger, larger grids, obviously the percentage overhead will be smaller. However, in real blocks, you will have a much larger number of threads in each dimension as well. So that will also move the percentage back up, right? The larger the block size, the more the percentage of padding you likely have. Okay, so this is just a base case. another reason why we would do memory tiling, do padding is because of coalescing. So in this particular case, let's assume that the coalescing units are 4 data points each. So if we didn't pad the data structure, let's say if we're willing to do the testing and so on, we still will run into coalescing problems. The reason is we will need, if we didn't have the padding, we will be starting the next row immediately at the end of the first row. And this will put 2 of the first rows and 2 of the second row elements into one coalescing unit. And this, in most of the current hardware, will cause some coalescing problems. And Fermi actually can use the cache to fix this kind of problem. So this is one of the reasons why I said the Fermi cache is actually designed to fix some of these problems. If you use Fermi cache, you should be able to still get coalescing effect, even though you have this misaligned coalescing units. Okay, this makes data structure padding less critical for for many applications. Okay, so let's look at the same thing with Coarsened kernel. When we merge multiple threads to calculate more than one lattice point, we are faced with 2 choices. Okay, the first choice is, let's say we can reduce the thread count per block. Going back to the previous picture, let's say we want to coarsen the threads. So if we are willing to reduce the X dimension to 2 threads from 4 threads, and then we have each thread to calculate 2 elements, then these tiles remain the same, right? So that's one possibility. And the other possibility is we still want to use 8 threads, but we want to have each thread to process 2 lattice points. In that case, the thread block will end up covering twice the amount of lattice. So the tile covered by each point, each thread block will become twice the size. So which will become the next picture. So we will end up with each thread block covering twice the number of lattice points. And when we start to pad data structure in this new configuration, we will end up padding more. Okay? Because each thread block will end up covering more of covering more of the lattice points. So chances are you will be adding more when you pad the data structure. And so this is the fundamental cost of thread coarsening. And in many usages, in this little example, you can actually end up spending about 92% more memory space. For large data structures, even for large data structures, we can easily be talking about 30% more usage. And that was one of the reasons why there was a pressure to fix this alignment problem for many real applications. Because the GPU global memory is already a highly contended resource. And you probably heard I think in both keynotes, the speakers actually mentioned that they were not able to fit all the data they want into the GPU memory. And if you start to pad your data structure, you get even less. Okay, so that's the contention. So with the Fermi cache and with you can actually coarsen the threads without padding as much, and that's usually how people do the coarsening today. And so this can be mitigated by reducing the number of threads in each block, X dimension in particular, but you can also have a limited ceiling because you cannot reduce your threads under the warp size. Otherwise, you run into real problems. So let me leave you with a simple quiz, okay? And I'll be happy to give you the answer after the lecture. But I like to at least get you to work on this a little bit. So let's say you have a 1,000 by 1,000 energy grid, and you have a 16 by 16 thread block. So let's say the coalescing unit is 64 bytes or 16 elements. So what would be the padding overhead if each thread processed one grid point? Any quick answers? Each dimension 16 elements, right? And then you have 1,000 elements in your lattice, right? Close. It's multiple of 16. Yeah, exactly right. Bingo, 1,008, because that's the closest 16 multiple, right? It's a trick question. I actually tricked half of my class when I was teaching the semester class. Everyone just said 124. Yeah, but if you have a thread to process 4 grid points, then you will be padding to 1,024. Okay, so work on it a little bit if it's not clear to you. Okay. So this is a slide from John Stone, and this is what he typically shows. The coarsening increases computational tile size, and the threads. Each thread will be processing multiple, lattice points that are separated by half. This is just illustration. The half warp size, which is 16 here in CUDA, and then you will have some padding overhead. Okay. So that's a grid calculation example. What I would like to do is put the whole thing together. So I would like to talk about the usage of thread coarsening, shear memory tiling, and register tiling in a real stencil code implementation. Okay, so hopefully this will put the whole thing together, and that will be the assignment that you'll be working on next Monday. Okay, so you know what, this is hopefully going to set you all up, and then tomorrow will be totally optional, right? Tomorrow, I'll be talking about 2 more techniques that are not going to be used in your lab assignment. So, we're going to be talking about a stencil code, and in particular, a 7-point stencil. So essentially, it's the center point and the neighbors from all the 6 surfaces. Okay, the surface neighbors. And so this calculation describes a class of nearest neighbor computations on structured grids, and is often used in PDE solvers, right? And I think both keynote speakers use stencil calculation in their talk. At each point of the grid is a weighted linear combination of subset of the neighbor values. So in the 7-point stencil, you will be having a linear combination of your 6 neighbors and yourself for the next one. Okay, and the optimizations and concepts covered, we will be using these things to talk about improving our locality and data reuse. So we'll be talking about 2D tiling in shear memory, and we'll be talking about coarsening and register tiling. The first 7 stencil implementation of this nature was done by Jim Demo's group. So when they first came out, my students look at it and say, "Hey, we could have done this." I said, "Yep, but they did it first." Okay, so remember this. It's important to do it first. Okay, so there are a few things about stencil calculation. Think in terms of a very large, a very large lattice. Okay, and it's highly parallel. The calculation of every lattice point is in parallel with everyone else, right? All you do is you take your neighbor's value, and then you generate your new value. That's the good part. The bad part is that oftentimes these things have steps. That is, before you can start your next calculation for the same point, you need to have everyone else in your neighborhood to complete their calculation so that you can use that value. Okay, so that's the bad part. And it's in general, whenever you have these kind of a very big amount of parallelism, But then you need to wait for everyone to finish before you can start the next phase. It's actually very problematic. And that's why people use all kinds of tricks like red-black algorithms and so on. But even that, there's still significant cost in terms of synchronization. So if you write your code as a single element code, then this kernel is going to do very, very little between each major synchronization. The kernel function is going to just take the 6 neighbor values and yourself do the calculation and then just go away, because you need to do a global synchronization before you can start the next kernel, right? So this means that the code actually would be doing very little work, and this sets you up for thread coarsening, okay? And each computation, actually I already talked about that. So there's also another bad problem with stencil calculation. It's very low. It has a very low computational intensity. If you look at the previous picture, what we're going to do is we're going to be accessing 7 memory data values. Okay, we're doing 7 memory accesses, and each memory access is going to result in a multiplication between the constant and its value, and then an addition, right? So it's not going to be a whole lot of operation you can do to the memory value. So every time you fetch a memory value, you're not doing more than just 1, or 2 floating point calculations. And according to what we have discussed so far, this thing is not going to get you very good GPU performance. You're going to be totally limited by memory bandwidth. So what we'd like to see is more granularity, less redundant work, and more operations per memory access. Okay? So the base case we start is the one thread calculates 1 point, and then we would like to be able to get to a much better point. So I already described this. So it's these 7 memory accesses, and then you will be doing a linear combination. And in this particular piece of application, the constant that will be used to multiply all these values is actually the same. So you'll have even fewer floating point operation per memory value you fetch. Okay? So let's start with thread coarsening. How do we coarsen the threads here? There are multiple ways, but the easiest way, which essentially Gym Demo students did, was to essentially take one of the dimensions. You have these 3-dimensional lattice. You take one of the dimensions, which in this case let's call it z. Okay, the z dimension here, and you have a single thread to calculate all the elements along that dimension. Okay, so this is even more than the DCS kernel coarsening. For large lattice, you will be calculating many, many, many elements along the z direction. Okay? Yeah, this is Volko's work. Yeah, exactly. And so why is this good? Remember, when you calculate a lattice value, you'll be using your neighbor's values, right? So if you use the same thread to calculate all the elements along z dimension, let's say you start with the first one. Okay, you start with the first one. And that first one is going to use 3 values. But the next one is only going to need a new value, not 3 new values. Because your current value becomes the neighbor value of your next one, right? And your current neighbor value becomes the center value. So you only need to have 1 more value in order to calculate the next neighbor. So this allows you to reuse data, right, in a very consistent way. You just you load 3 first, and then every time you move to a new value, you just load another new value.
This is a 3-dimensional stencil.
It's a 3-dimensional stencil.
So if you load if you're computing for the next phase, you do get reuse, but you don't. You need more than that 1 new value.
You're absolutely right.
Okay.
So that's exactly this. Okay. So oops. can we reduce the lighting a little bit? Sorry about that. I meant to rewrite the whole. I'll reproduce the slide. So you don't reduce all the 7, okay? So what you end up.
You still need 4 new values every.
That's exactly those 4 loads, okay? So you start with 2, bottom and current. Okay, let's assume that we're going from bottom up, okay? So you load the bottom element, you load the current element, and then you load, you load the top element. So these are the 3 you start, right? And in order to calculate each element, you will actually be still doing 4 memory accesses to your horizontal neighbors, okay?
Plus your 1 person.
And plus your next one. So on average, you will be doing 5 accesses rather than 7 accesses.
Right, you're reusing 2.
You're reusing 2. Okay? So this piece of code will allow you to reduce the access by 2. And when you finish with your current point, you will be moving your current to the bottom because you're moving up now. So what you have now is the bottom value for your upper neighbor. And then the top becomes its current value. Okay? And then you would load one more element. You load that one more element on the top to the top. You go back and you still need to load 4 more. Great observation there. Thank you. Yes?
Instead of fetching the top at every iteration, wouldn't it be better to fetch a lot of them?
Absolutely. That's the next step. That's exactly the idea. You got it, exactly the right idea. So you see, don't you wish that you did this before Balco? Yeah, you publish it. It's a very popular paper. It's highly referenced paper. Okay. So what I'm also hoping to do here is to make sure that all the grad students here understand that the best kind of work is actually the kind of work that when someone else look at it and say, oh, it's so obvious I could have done it.
But then they don't get published.
Exactly. Not really. You can still publish. Some of the reviewers are a little bit. I'm not going to get. I'm being recorded. I'm not going to say anymore. But that's the best work. In fact, when I review papers, I explicitly do this. I check whether I feel that it's so obvious that it shouldn't be published, and I give it my highest scores. That's what I do. Okay. So the load. So assume no data reuse. Along the z direction. In the previous case, then every element requires 7 input elements. But if you reuse, then you go down to 5. That's exactly what we just talked about, right? Okay. Now, going to your idea now. Okay. So we can actually do some cross-thread data reuse. Okay. And if you look at this from the horizontal point of view, remember we were loading these 4 elements, right? We're loading these 4 elements for calculating that center point. And each internal point is actually used to calculate, 4 planar elements at the same, for the 4 neighbors. So there's really no. If I look at this value, it's actually being used by 4 of its neighbors, right? So when I go up in the z dimension, I'm loading my own next value. Okay, I'm loading my own top value, right? But this top value, once it becomes my center value, it could be used by 4 other neighbors. And that's what you wanted to avoid, right? So that's exactly how we're going to do the next one. We're going to be tiling the horizontal data by doing barrier synchronization across threads that are doing barrier synchronization of all the threads that are going up at the same time in the same block. Okay, so think about this as a block of threads. All of the threads are going up at the same time. By adding barrier synchronization, we can make sure that they go up in lockstep, right? Remember those phases that we talked about for matrix multiplication? Here, we use barrier synchronization to make sure that all those threads in the block will process one horizontal plane and then do the next one, do the next one, do the next one. Make sense? When that happens, then we can actually just load all the elements in that horizontal plane once and have all the threads who want to use a particular element, which means 4 of them, to enjoy that element, right? So this allows us to reuse the data 4 times, okay? Even better, you don't even need to load it once, because by the time you want it to be in your center position, a thread has already loaded as its top element in the previous iteration. All you need to do is to move that element from the register into shared memory so that 4 other threads can use it, okay? And that should be the code that you'll be writing on Monday. And essentially what happens is that on each phase, maintain 3 slices of relevant input data in on-chip memory. So, but all the 3 slices are actually in registers, if you think about it. Because every thread will have a top, center, and bottom. So when you look across all the threads, you'll have 3 slices of data all in the registers of those threads, okay? Meanwhile, you also put the current elements into the shared memory. So remember, when we move up to the next one in the previous code, we load the top, right? And instead of doing this, we will actually be moving the top element into a shared memory location here. And then you just loop back, and the code here will be used in the shared memory location, okay? And after this, you end up with only 1 memory access per element on average, okay? So that's how register tiling, thread coarsening, and shared memory tiling all come together, okay? And it's a very useful idiom for, for most of the stencil calculations. Oops. So here's some interesting, there's a little bit of a dirty laundry here for, for stencil code, okay? We have these ghost cells in the stencil code. Essentially, let's say if we have a thread block, each thread is processing 1 element. The problem is, if a thread is processing an element at the boundary, then you actually need to have 1 neighbor value, right, in order to calculate the element value here. And this is called skirt cells, halo cells, multiple names, right? And so one way to do this is actually to load the halo cells into the shared memory. Okay, that would be one way to do this. And so if you do it that way, then what happens is when you move up from 1 level to the next level, you will be writing your own value into the shared memory. And also, you need to make sure that there's the boundary ones also load their halo cells into the shared memory. And if you did this, then you don't need to do a boundary test when you run the current when you do the calculation. So there's a cost to these halo cells, okay? And there's a very easy calculation you can do. So let's say if you have n elements in 1 dimension and m elements in the other y dimension and p elements in the z dimension, in order to load halo cells, in general, you can end up with n plus 2 times n plus 2 times p plus 2. 2 is a small number. Okay, 2 is a small number. However, it's not such a small number for the current generation of shared memory sizes. Okay, and you can, and also this number can actually give you some, sizable overhead in terms of the actual loading you need to do. So let's take that previous example. If we have n equal to 16 and m equal to 8, then each slice will calculate 128 of these output elements. But then we need to load 180 because of those halo cells. Okay, we need to add the 52 additional ones from the surrounding cells. So instead of 128, you end up loading 180, and you will be the original code without loading into the shared memory will be loading 640. It's 5 times these things. So you end up reducing the access by 3.5 times rather than 5 times. So that's why halo cells can be very costly. It doesn't necessarily just add to the shared memory you need to use for them. It also adds to the number of loads you need to have. And that actually reduces the bandwidth reduction that you can achieve with your tiling algorithm. And why do I say that for the current generation of shared memory, 2 is not a small number? Because the current generation of shared memory limits the number, the size of the dimension of these tiles you can load. Because these tiles, the multiplication makes these things grow very quickly. So if you have a few K of shared memory, if you have a 2-dimensional case, then your 2 can be somewhat significant. And if you have a 3-dimensional case, 2 can be very, very significant if you work out all the numbers. Okay? Yes? Yes. You can. The question is, do you get any branches from the halo cells? You cannot avoid branch either way. You either need to have some branch at the at the end of the kernel when you move back to the loop where you put the halo cell in here, or you need to have the halo cell. You need to test the halo cell here if you didn't load the halo cell. So one way or the other, you will end up with some additional branches. Okay. The only way you can avoid branches is by always just go out to the memory in the most bandwidth inefficient version. Okay, and this is definitely a worthwhile cost. Having a branch here to save memory bandwidth is definitely worth it. Okay. I think I'm almost there. So in Fermi, this is actually one of the grad student nightmares. In the previous generation hardware, it was almost always better to load the halo cells into the shared memory. But in Fermi, it actually become the other way around. So it's actually better not to load the halo cell elements into the shared memory. It also allow you to use the cache better. So a lot of the code actually changed. So if you look at, for example, I'm not going to give you that pointer because you need to write the code. But after you finish the code, you can actually go to the Illinois website and look at the stencil code benchmark, and you will see that the benchmark has changed from loading the halo cell into shared memory into not loading halo cell into the shared memory. So that concludes the talk, and as promised, I did make up a few minutes. And this is an illustration that GPU acceleration is also good for lectures. Okay, so is there any other question? If not, yes.
My impression was that your example was overly pessimistic because your grid was too small. So of course, having 2 halo cells is significant, but for a larger mesh that I think that wouldn't be such a.
That's exactly the point. If you can produce a very large tile, then the halo cost is going to be less. Yeah. But the tile size is limited by the sheer memory size that you can afford. So that was my point. Excellent. Yes.
In the previous lecture, you said about the way that the threads reading from the global memory.
Yes.
And in this example, some kind to suggest that we arrange the 3D dimensional array
Yeah.
in a one
Okay.
dimensional array
Yeah.
to ensure that the threads is not reading are not reading from not
Okay. Yes. Okay. Yeah. So that's a memory layout question, right? So you have these three-dimensional lattice, and how are the lattice points laid out in the global memory, and how do you get coalesced accesses, right? Good. So this is what this picture is meant to show, and I actually skipped this part. I was trying to make up some time, but you always come back. Good question. So if you look at these are the seven points, the 6 neighbor points, and 2 of the neighbors are in the x dimension, so they're right immediate to each other. Okay, the y dimension are a little bit farther from each other, and the z neighbor are even farther away from each other. So the reason why the final version is going to be fully coalesced is because every thread will essentially only be fetching its own element, if you think about it. All these neighbor values are being collected from other threads in the shared memory. So that's why at every step of your z-dimensional elevation here, the memory accesses are always going to be coalesced because every thread only needs to access one element, and all the neighboring threads will be accessing physically neighboring locations. Okay?
Yes, but you move in the
Z-dimension, yes.
But you also can move from the x direction.
No.
Right? The question is, what is the best way to move?
Yes. The reason why you move in the z dimension is because it's the slowest changing dimension. So that's why when you move, you load one element, and by the time you load your next z neighbor, it's within the same thread, right? So that's the least potential disturbance to your coalescing, because you'll be accessing you will not be accessing any neighboring location at the same time with your I'll put it this way. Those neighbors are so far away that there's no way you can coalesce them. So you may as well just use the next step to access it, right?
What do you do on the extra tile? That you can't read shared memory with a value adjacent.
The extra tile.
Yeah, if I have a tile like this and I'm here,
Yeah.
This value wasn't loaded by anyone in my thread block.
That's right. That's what I'm saying. I was mumbling about this.
I thought that's what
Yeah.
you were talking about.
Yeah, so that's why you need to have some extra code here
Yeah.
to load it in.
Okay, fine, yeah.
If you didn't have the extra code to load it in, then you need to actually have some extra code here to test whether you're at the boundary.
So you load a halo for absolutely every
Yeah.
tile.
Yeah, so in fact, this piece of code, this piece of code will need to become an if then else. And if you're inside, then you'll be using the shared memory. But if you're outside, one of your value will be coming from the global memory directly. One way or the other, you will have if then else. That's why I said you cannot eliminate if then else one way or the other. Yeah. Very good. If not, thank you very much, and hope to see you tomorrow.